where he's in the agroecological research unit.
Yep.
He's a hydrologist with that unit who actually got his degrees at University of Iowa, even though he's now in the Iowa State zone. So he's going to talk to us today about rainfall intensity and a bunch of interesting intersections between physics and soil and outcomes we care about on the landscape.
All right. Thank you, Anna. And thanks for having such a nice organized day and great with meeting with everybody and taking the time. And if anybody wants, send me a note afterwards or whatever and talk collaborations or whatever you would like. So late afternoon talks, make it interesting. Okay. Wait, don't read that out loud. Okay. So title, how management impacts the functionality of surface aggregates and resilience to rainfall intensification. So if you can get enough buzzwords packed in a as I was saying. No. So here's a little slide, a picture here from some rainfall work we did. I like it. Kind of shows a group of people standing in mud trying to get some results and wondering why you do rainfall. No, just kidding. Anybody that's done that kind of work can appreciate that. It's tough work. It's great. You do get some information from them. But let's, how can we pull a lot of that data together to tell a good coherent story that you can use from a farmer and say, hey, do this practice and so forth. So today I'm going to talk about some of the, see if I can, that just stay up there, maybe? Does that go away or?
It's possible for it to go away. Let's try that one. And then that.
Boom. Thank you.
I don't remember how you get it back.
Because I wouldn't even guess what my titles were called if not. So some challenges, some of my findings, and maybe some thoughts on where the future direction should go for some research. And all of this will be tied to near surface, so upper part of the soil and how that interacts with different weather patterns, different climate, and the response of how management can be changed to be able to influence that upper interaction. So US Midwest soils are productive. So that top right plot over there, that's just showing grain production of corn. And the big takeaway is the darker the green, the more corn is being produced there. So right within our zone here, that these soils are all, mollisol just derived. I mean, we're able to throw stuff in the ground. It's rain fed generally, and we produce a lot of grain within them. And this plot here is showing, we're coming along with our genetic potential of the seeds due to different practices and improvements. We're rampant yields. One thing about yields, as you increase, this variability becomes very up and down. A lot of that is driven from climate variability / weather. Jerry Hatfield, when I talk with him, he says climate dictates the type and location of the crops grown. Weather controls how much you get out of it. So I always like that differential because people are saying climate, weather patterns, and so forth. But as I said, those yield gaps. So what we're not being able to get from our yields is an impact on that interaction between the climate and the management through erosion processes, through enhanced mineralization from too much tillage and so forth. So some driving questions for this research. If you drive across Iowa, I'm sure a lot of these lands here, we see rainfall coming down very fast, and what's left is these ponds. So we get our name for those prairie potholes down in Ames, but basically what's happening is it's not putting the water in the ground. And we're left with kind of a sealing effect of that near surface in response to some of these changing patterns. So this top left plot here, it's just showing that we are seeing increased precipitation. However, it's not just coming, if you had a 5-gallon bucket or I guess a trash can, by the end of the year, you're probably not going to see big changes if you're measuring at that. But when we do see is if you look at the intensities. So we're seeing a shift towards more intense rainfall coming. And what we have at that near surface is going to become more impactful for what kind of a response we're going to get. So some questions that could drive us is, what's the role of surface aggregates in the resilience to this increased rainfall intensification? If I'm looking at my fields, what management can I do to promote stronger, more resilient aggregates within that top 5 or that active layer? And then another question is, how are rainfall patterns changing? So are we looking at storms coming where the rain's coming in the front end of it? Is it, dry in the beginning, or is it wet? So if you could characterize the storm pattern, and then what's a response to that? And then looking at, for trend wise, are we seeing more of these start to develop? Are they shifting towards different seasonal points, and what we could do about it with management? So the importance of the soil active layer. 2 different systems. And some of this is coming from engineering. So everything's finite element, non-deformable bodies and so forth. So that's how I was initially looking at the soil structure. And then working with Cindy Carbondella, was kind of an aggregate expert. She was telling me that this is actually living and breathing soil. So we smashed heads a lot over the years working with her. But anyway, what it comes down to is I'm kind of fusing some of those things together. So high biological activity is going to promote, high microbial biomass in there. And what that structure is it's providing, shelter, food, and security for those microbes. And when you got weak soil, it's continually getting thrashed and everything's washed out of the way. What you want to do is provide a good home for them within there. So strong aggregates are going to promote more water going into the ground. Weaker, low biological activity, more vulnerable, more able to constrict and pore network collapse during these rain, and it's triggering erosion events. So I wish everything, what I like to do is dabble in some modeling, numerical modeling, but the importance of the soil active layer. So if everything could be like those little marbles, right, for particles in there, you can just kind of, you can visualize water moving through the soil. However, it's not, there's collapse in here. What we did here, this is an X-ray microtomography, and this is taking just a soil core, like some PVC pound in the ground, and you're looking at a scan of it. So here we're going this way into it. What you see is like there's bits of organic material, there's weird little micro pore networks in there. And in this study, I was trying to find a way to use this, get a 3D image, and then use a 3D printer with some actual soil material to be able to replicate these networks in there, and then do flow column experiments to go through there and look at it. Just because it took so long to get these images, I'm going to show this one too. Now we're moving through the plastic or the PVC, but you can see that it's very dynamic, and your management really dictates a lot of those networks. So one, it's nice to think of it as those elements or those marbles, but in reality, it's much more complex due to seasonal compactions, tractors driving over it, and so forth. So that's looking at a point scale. Now let's look at the landscape. So say you did have some of that restriction, you can have concentrated flow starting to develop. Landscapes have a certain skin across them that water is inherently going to flow across, but you could get channelized pathways, you can get material coming in. You have different controls. Initially, you can have your micro roughness control of it, which is your grain roughness. That can move to a larger scale and look at oriented roughness, so tillages, and how that's going to dictate and shape the water movement. Basically, what you can have is material moving from top to bottom, causing a lot of the heterogeneity that we see in these fields. Moving even bigger to a bunch of these fields. So this is looking at a catchment here. This one happens to be up near Iowa City, so it's the Clear Creek watershed. We had monitored this for almost 20 years up there, but looking at each of those are kind of your farm fields. And thinking of it as a system, if you apply this water to this system right here, what is going to be the response? So everything is going to have an inherent ability to be able to push water through a system. This is I think this is a great schematic here. This is from Keystra, talking about the differences between structural connectivity versus functional connectivity. So structural is like, it's It's an inherent connectivity of a system. So whatever properties form it, or say if I have this water up here and I accidentally spill it, it's going to move a certain way, right? Now, what happens with these fluxes, or this part of it here, what the functional part is that management and stuff is going to induce sediment fluxes, runoff fluxes, nutrients, and you're going to reshape that. And there's a constant feedback between these systems. And one thing to think about, as that's bouncing back and forth, more intense management, it's reverberating with a lot of energy. When systems are in balance, your water is able to route and move it through the system. However, when you get a system out of balance, say you have practices up here that are causing that restrictiveness of that upper layer, they're turning into parking lots, and that applied rainfall is going right in and it's overwhelming your drainage networks. And at the end, this is what we've seen around 2009, where we had, rising 13 feet. And this happened many times during the year there. So it was common to see over the top of these bridges, just like this. It's a flashy system showing that there's the management and everything it's out of bounds within that system. So looking at some of those factors, or kind of putting some topics together of a couple things I've done. We're going to categorize this by raindrop impact. So one is looking at that energy. How's that energy being applied? How does different intensities dictate that? That ties in well with the soil water interactions within that active layer. So what's the response of that upper surface? And then again, moving towards that landscape scale, how is that being maneuvered through the drainage networks? Some edge of field monitoring, and lastly, if time, a little bit on some numerical framework I put together to be able to categorize some of these storm patterns, and for us to take a look at how are those changing in time, and what's the reflection of the runoff and sediment rates coming off of them. So raindrop impact. I like this one here. This is from a rainfall simulation. Takeaway for me, or my theory on it, is these raindrops come in all different sizes. It's the mass of them, and they're hitting the ground at a terminal velocity like 20 miles an hour. But the size of it is almost reflective of the size of your aggregate structure within there. So it's not just the rain hitting, like us, it's you're hitting something at a much finer scale. So dislodgement, changes the complete roughness of this bed, and it's going to impact your flow dynamics. Here's a study that we had a guy from Brazil, a professor, Lima was his name. This whole thing was rainfall, and a lot of people can't afford these expensive disdrometers and different laser techniques to be able to measure what is my rainfall distribution. And then everything is based on an assumption that, well, this drop falls this fast and this drop falls this fast. In reality, you have all these different sizes and they're hitting the ground at different, so it's very complex. And even if you do get a disdrometer and you get a cube of air here and you say, this is what your drops are, it could change with the blow of the wind, or, so a lot of that forcing is going to change. So what we thought was, let's devise a little simplified method, almost like a black box approach. And we're going to call it the helicopter rain gauge. I think for the paper, they didn't like that, so we called it the dynamic rain gauge. Yeah. But, hindsight, the thing spins about right here, so shin buster could be another one. But basically, this is all these rain gauges. The one in the middle is going to collect all of your rainfall. And then as you move out, like if that old game where you launch people, or like a merry-go-round, putting them out, broken collarbones. As you move out here, that velocity is going to go faster and faster and faster, the angular velocity. So a way to calibrate that, or what we found was, or his idea that he came up with it, was this angle on it was when he was driving to a stop sign and when it was raining, the back window would become wet, at that angle there. But as you started to drive, you'd hit a certain speed, it'd be dry. So now you'll probably think about that when the next time it rains, but I don't know if we even have those shape of windows, but when I was, those kind of cars I drove at least, but. So in the end, what this does is you change, each of these have a velocity, and you spin it fast enough where the rain will get collected maybe to that outermost one. And when that one's dry, That means you're encapsulating the terminal velocities of all those falling drops. Took me a long time to wrap my head around how that actually works. But what you do is you translate rotational velocity to this velocity, and the components of a kinetic energy, you get the mass, and then that velocity, in each of them, you get a kinetic energy. So you can measure that rainfall within here. And it was agreed well with the disdrometer, and we're able to like turn this on. This is how I calibrate a lot of my rainfall simulators now. Another thing, looking at surface aggregates. So I've got a little rainfall simulator set up here. This is when I was at the erosion lab. This is probably the newest generation of rainfall simulator. It kind of takes that Norton ladder, and now it's confined about like this big of a thing. So it's got recirculating water to be able to keep itself, instead of this whole recirculating system that you'd have huge amounts of water coming down here and you're trying to pump it back up to here. Nightmare. This one here uses a little microprocessor in there. I got a remote I put in my pocket. Beep, beep. And then it's like, I could do 32 different rainfall intensities. It uses Arduino little technology to be able to come up with some creative ways to turn the motor, reverse it, turn it, and you can program it to do a lot of things. What this simulator does, it's up here. All those drops are terminal. I use the helicopter rain gauge now. But anyway, what we could do is we could place aggregates on here, and I wanted to look at the breakdown of them over time. Here you can see underneath here, kind of a collection. And I'll show you a plot, I think. Yeah. So the physical processes that are going on here. So the first part, when aggregates at the surface are hitting, rain's hitting them, it's just dominated by raindrop impact. So you just got that energy hammering into them. And then as a storm continues, water starts to soak in. They can, overcome those internal forces, causing slaking plus this raindrop impact. And I'm going to show this here. I had 2 spots in a field where I collected some soil, low carbon, high carbon, and I would isolate those size fractions. See if there's like don't look at this plot on the left yet. Imagine if I took a scoop of soil and I isolated these fractions, right? Because I'm thinking I'm going to try that marble game again, because everything should have a certain shape now. But so how do those break down? This is collected every 5 minutes during the rainfall. This is how much is left. You see this sharp descent as you go through there. So fine. So by the end of it, after 5 minutes, you're like 60% left of this versus 20. But everything's got that pretty much degrading trend line. And what that was telling me was, if I'm looking in that upper surface, as those are collapsing, it's going to cause a restrictiveness. So I was talking about this concept called time to clogging. So my theory is there's a characteristic diameter within a soil that probably shifts this way with management and texture, whatever dimensional axis that needs to be. But once it gets down to that characteristic scale or that characteristic diameter, that's going to trigger runoff. So I'm going to try figuring out this thing called time to clogging, or time to ponding has kind of been used. So I'm thinking time to clogging. So here you see higher carbon content. You see much more resistant to that same raindrop energy. Water stable ags. So that, looking at an air dried and dunking them and looking at the response to that, I call that kind of the worst case scenario. And it's also more reflective maybe of these processes as water's moving in. I found a relation that, this here was tied to this lower carbon, lower infiltration, lower actability. This one over here, higher and higher. So showing me that infiltration, that kind of a clogging of the networks, it's tied in. This led to me buying a bunch of these automated Saturo infiltrometers. And now I'm currently trying to say if that's get a lot more points in that trend. Also tying it to some landscape processes. So looking at a hill, this axis here is slope. So high slope, low. And this is how much aggregate or how much carbon is within an aggregate. So again, looking at each of those, this red circle is going to denote if I was going to take just a bulk sample and you go roller mill it and you turn it in for analysis, that red circle is the number we're getting. However, you see that's quite a spread for how much carbon is in those aggregates. So that could have implications to during rainfall events, what size fractions of aggregates are flowing, what's breaking down. So kind of help to understand that. And then also look at the trend of the gradient effects. High slope, low, reflecting maybe raindrop stripping or fining over the time, or maybe deposition over here of some of that finer fractions that hold and encapsulate more carbon. Continuing with some landscape process, here's kind of a setup of some previous rainfall simulator work. Again, this is what kind of got me on this was I would have been fine because in models it says that everything moves as primary particles, that there's no aggregates. However, now knowing that there's that much difference in carbon, now I need to know what size fractions are moving to be able to look and correct for some of these estimates. If you're looking at using models like WEP and so forth like that, to improve their transport, the routing mechanisms of the sediment. So different experiments looking, here's kind of the dimensions of the plot. Usually we'll have this all screened because wind really affects things. Moisture sensors in here to determine when you reach kind of pseudo steady states of runoff, when your hydrology is coming into that. And then at the outlet there, we're taking samples discrete to measure your runoff, looking at just kind of some differences about different orientated roughnesses and how that's dictating some of the flow. Backwards. Just a couple, just looking. Some setups here, we've used lasers to be able to try to go down there. Hopes were to try to quantify real flow depths, doing real measurements or injecting different dyes in them, measuring transport times and lag times, and trying to get a variety of different systems to be able to see some of this. This was a project we were doing, trying to improve the WEP transport model, erosion prediction. Now we've kind of got a version, we just call it what used to be WEP. And anyway, they haven't updated it, and it looks like they're kind of moving on to like the Russell, like that. So if anybody's interested, we got a really good model that can actually simulate a lot of these processes of step and pool. I think, Anna, we were talking about, some of those impacts there as the different roughness elements here and break and burst throughs and stuff like that. That'll be happening there. Spillover erosion, head cutting. And there's just some of the dye tracers that we were used to be able to improve some of our formulations. This is a busy plot, so I'm just going to gloss over it. What I was trying to find was, if I was able to find and track what particles are moving in these storms, I want to tie it to a nutrient without having to measure nutrients all the time, because we didn't really have the availability to measure nutrients. So that was it when I was in engineering program, nobody measures nutrients. It's like, we didn't hardly measure sediment, but what we found was the enrichment ratio. You could connect the physical texture components by looking specific surface area of all of your sediment. And that means what? It means your finer clays and those organics can hold a lot of surface area, right? And they've tied very well to carbon content. So in the end, we're take a sample, we'd measure with a cetograph and look very detailed particle size analysis. And here we were able to find, pretty good relation. Some items that we're not handling well, contour ridge. So a lot of those dynamics of the step and pool systems, showing that we need to improve that. So we're not able to do it yet because it's very episodic. We don't know when they're going to break through and release to the next check dam of material within there. So more work there is needed. When I was in Indiana, I walked in during the shutdown, and this huge rainfall simulator looked like it had never been used in my life. This is a famous one. So this is a 12 meters long, 5 meters wide. They call it the big box, and it's awesome. Except during that time, they left water in it, so everything kind of needed to be redone. So I spent time, this has 54 different rainfall nozzles to be able to simulate this. It's quite a feat. And you can adjust and you can push subsurface, you can change the water table dynamics, and you can collect and sample, you can look seepage. So I'm currently have some experiments planned. I'm collaborating on now. I got it all ready. It looks better than this picture, but I couldn't find one. And we're going back and we're going to be looking, we're using cell phone cameras, like these new iPhones, they have like LiDAR sensors in them. And we're going to look like micro, scale and see if we can find changes in roughness over time or just different things like there. The best part is it's inside and you don't get nailed with all this. Oh, it rained. Okay, great. You could control the conditions much better. Everything comes at the outlet. So if you want to see outlet coming out, that's something. I mean, it's garbage can, garbage can. You got to be ready. Before I came, for some reason, they just let it just flood everything. I was like, okay, we can do better. So I got pump system. Edge of field monitoring. So don't want to do that many rainfall simulators. No, just kidding. Now I'm moving to edge of field. So the whole thing with that is rainfall intensities. Everything's fixed with these experiments. You pick an intensity that everybody else does in the literature, you rain on it, and you do get some information, but it's very specific to that site. We have developed some relations, but where it needs to move to is more of this field monitoring and with natural rainfalls. Why? Because rain doesn't come just like this, like I was saying earlier. There's a pattern to it and so forth. So this is a site up in Indiana. We've got a bunch down in Iowa, but I started this formulation when I was there, looking at two paired little basins there, roughly the same size, maybe 5 acres. And no, maybe 7 to 10. And at the outlet here, you're monitoring real-time runoff. You got an ISCO sampler, which is grabbing discrete samples to be able to sample sediment or what's in the runoff. You could do particle size, sediment, nutrients, and so forth, and see the response. We also have 1 minute rainfall intensity data available there that gets averaged to 5 minute. And then the whole point of that was seeing rain, runoff, what's the interactions. So that's a busy plot too. All right, example data. This is it here, it's in 10 minutes. Here's my rainfall intensity, 77 millimeters per hour, 6, nothing, 25, now that we have this availability for higher resolution data, how can we categorize what an actual storm looks like? Because it's going like this, it's not these perfect, here's the rainfall intensity. In reality, it's changing a lot. So each of these have a certain storm pattern. So this is plotted here. So high until low. Some of them have little dry periods. So this is pulling on Huff, the old 1967 quartile method to categorize storm events. And I think it's brilliant work. I think a lot of people have gotten away from it, but I think there's a lot of hidden stuff in there and able to categorize and quantify storm patterns. What his theory was, you could do it into 4 patterns. One is heavy in the beginning, maybe it starts to get heavy, 3rd quarter, and then the 4th is, boom, there's your peak. And based on that is to look at what would be the response if I could categorize a storm, then I could look at the runoff and then tie in sediment and see the response. If I'm gonna be taking some of these samples of the field, can I use some of those storm patterns to help be more intuitive seasonally to be able to trigger my sample collection so I could capture the whole hydrograph that's being routed through for the runoff? What do I mean? So if this was the rainfall, this is a theoretic one, but here's runoff over time and then goes dry. So how can you do interval based, or are you doing like a composite base in there? A lot of this here that would be triggered from that would release a lot of that fine materials. You may be missing a huge surge of whatever nutrient of interest or herbicides or whatever would be we wash through there. So how can we be intuitive and be able to predict how to sample for those and capture both the rising and falling limbs of that? So this just kind of shows what it is. It's rainfall intensity, fills in any gaps. It identifies individual storms. So based on kind of that shape there, if there's a critical duration. So it flags the storm. It has a profile, quantifies into 1 or 4 quartiles, as I said, from either beginning heavy towards late, calculates the erosivity using kinetic energy, and you get an event summary. For runoff, same thing, kind of takes that data. Now I'm going to group it with that storm so you can have side-by-side comparison. This is just showing, this is over a 10-year period, but a lot of them, this is non-dimensional analysis. So it doesn't matter if you know like how long it is, you're just going storm duration and dimensionless rainfall accumulation. So here you see quartile 1, a lot of them fit into that pattern. Quartile 2, here's where I'm showing that. 3, and then this is that late season. And if I took kind of that average of each of those, this is kind of what the characteristic storm shapes would be of those different storm patterns. And then you can look at what quartile is producing the most erosive based on the wind intensities and so forth. So you can get a lot of information. One thing I did notice was, so quartile 4 was responsive for much higher erosion within a lot of these fields. And what I've seen is a 50% increase within that 10-year period from start to finish. And a majority of that is becoming in this late October, September, October range, showing that, you know, that you should be mindful of harvest, what's going to be on the ground at that time, because this is a very vulnerable time for the soil. But now I need to use that for like a bunch of observatory networks that we have. But my whole thing was, this is it, my little trial run. And now I can put it out for others. LTAR, since we're doing LTAR, wanted to throw that in there. Using some of baseline sampling and looking at infiltration and looking aggregate characteristics over time. Basically, we got a site up here in Williams, Iowa, and it has been for 70 years conventional managed. And then in 2016, it converted over to a stripped reduced till with rye cover crop. But I think it's important to note this kind of the historic imagery of it. I like seeing all those little parcels of land, but you see kind of braided networks. So kind of an active landscape. Through the 50s, like those 5-year rotations started to become, as livestock and stuff were pretty prominent through this area. So, and then as you move here, and then it became kind of, oh, we're just gonna go just corn and beans, you know, larger. Then it became just corn on the top and then just beans. So what we're doing is going out in these fields and doing gridded sampling, trying to capture some of those networks. I think the next slide. Ooh, this has animation, that's right. Flow path. So this is elevation with some LiDAR data. Basically the field, sorry to ruin it if some arrows pop up, it goes that way. Yeah, it does. That's the way it flows, but you know from those other images. One thing to note, in the beginning when it was conventional, this was the microbial biomass carbon. So taking that gridded sampling and looking at it to 2018, just within that 2-year period, on a field average, it increased 150 milligrams per kilogram of carbon. We had an increase in 10% within that, was it the first year? Yeah. And we just went back and sampled this field now, 2023. So it's going on the 8-year mark. And I've already seen that there's been 40% increase in water stable ags due to this adoption of this more conservation practices and so forth. Yields get to be more homogeneous as well. So back to that whole thing with the yield gaps, you start to dampen that intensification, you can get more, your yields be more dependable or predictable, I would say. So with that summary, landscape processes shape the spatial distribution of soil properties, nutrient cycling, and production. So again, if I'm going to make a wager on something, I'm going to look at the aggregate characteristics within that surface. I think if I was a doctor, medical doctor, you could use those as x-rays. One, by looking dry distribution of aggregates, you could tell tillage intensification, how that's shifting it towards finers or here. which kind of gives you your starting point, what would happen before the event hits, right? And then the stable ags kind of give you what's going to happen in response, and it kind of infers some points within a landscape where a lot of those landscape processes would be triggered from. I think it's important to move towards identifying rainfall patterns, quantifying and categorizing them, so we can better understand any shifting trends and tie them back to a lot of the erosion and runoff processes, so we can make better informed management decisions. And with that, I'll take any questions, or here's some acknowledgements of whatever some of those slides were there in collaborations. And it could be you if you want. Yeah.
September and October seem to be the most vulnerable months. What about snow melt? Still don't have vegetation on the landscape. Now you're dealing with frozen soils. How is this all impacted with the aggregate side?
It needs investigated. I had done a little pilot study on looking some of the dynamics of that snow cover and that early melt, because what it is in hydrologic terms is it's almost acts as conduit flow instead of open channel. It's almost pressurized in there because it's, with that cap on it. So when that's moving, you get a lot of erosion. And I mean, you'll see it like in the rivers at that time. It'll be chocolate milk with that early season. And I think a lot of that is, but yeah, that needs to be.
So when is your greatest erosion? Is it that spring thaw, or is it in the fall after everything's harvested?
Traditionally, May,
Okay.
I would say, right there where most convective storms present, lack of height on the crops, generally a spring tillage to be able to, break it up and stuff. And then that was traditionally like, that's your most vulnerable point.
Go back to the slide with the gaps. What were the conservation practices that led to the increases in soil carbon in there?
So that was, it was a strip till, and then it was rye cover crop added. Yeah.
I have a big scale question and a small scale question. The big scale one is, so you talked a lot about estimating these rainfall intensities at really minute intervals. Do you have to have one of those helicopter rain gauges? How much can you do with the satellite imagery to estimate that stuff?
I think you can get some large, I just realized I got on here, never mind. The question was, how do you deal with the spatial scale of, do you need to get really small measurements of rainfall intensity, and how does that work with like a larger? There's gridded intensity data, kilometer based, I think you could start there. I think that it's, depends on the temporal resolution of it. That's a big one.
You maybe can't get the high temporal resolution data, if you're using satellite data or sort of the broadly available data sets.
Well, I think most of the sites are getting able to at least give 5 or 10 minute data, which I think is suffice. I think 10, it shows that 10 is, you're able to capture the event. That's what I've seen.
Then my small scale question is about the aggregate stuff you showed in the beginning, and how your high carbon aggregates broke down more than your low carbon aggregates, essentially. My question is, can you have the same amount of carbon, but different effect, like different strength or function in that aggregate? Like, could you have a 3% carbon aggregate that was stronger than a 3% carbon aggregate?
For sure.
Okay.
Yeah. It's going to be inherent of probably the soil characteristics, textures, to be able to hold it. Because some soils have huge amounts, depending on historical or legacy.
And I got a question.
Yeah.
Can you hear me?
Yes.
This is Satish Gupta. So in your intensity measurements, did you try to separate out the effect of soil wetness? Like you start the experiment, soil gets wet, you continue measuring the intensity effects, What about the soil wetness effect on that?
Yeah, what I looked at was number of dry days, number of wet days, just kind of at a higher level where I was looking at data. If we're doing like a plot experiment, yes, we were very much tracking before we did any initial run of that. We made sure that they were at, you know, comparable moisture contents. Because
Oh,
that's
but
very sensitive.
How about during the experiment? You know, the wetness is changing as the
Yeah.
intensity. How did you account for that?
We have sensors within there in the plot at different, you know, at the lower midsection and top slope there. And then we would monitor those over the experiment. And, you know, what we're looking for is when that hits kind of a pseudo steady state, that would infer that our hydrology is starting to reach that, you know, like a steady runoff point, right? And I was talking earlier was, you know, usually your lower parts of the downslope, that does it quicker, right? But as you
Right.
move to the upslope, you want to make sure that that top part of that section hits that, because it's generally starved because you have no inflow. And it takes longer for, you know, morphology and stuff to reach that top point as it propagates upslope.
All right, thank you.
Yep.
Question is that photography data was very cool. Could you tell us a little bit more about how the data was collected and processed?
Yep. So the PVC cores were collected, the top five centimeters, and taken to the Center of Non-Destructive Technology. And then he was able to scan those. I got this guy he just started there, so he was scanning everything. Like, I seen he got a bucket of Kentucky Fried Chicken. It was like scanning like legs, and I'm like, "You're doing this? Like, how about you scan this soil core?" So he's like, "I want to see if it works too." So, but yeah, he would scan that, and then what was given was a 3D, basically large data file that, you know, has the three dimensions, and then you can use that for almost like a porosity. So something and then void. I think you can distinguish those two things. So that would be kind of what that matrix of data would look like.
When did you take the course?
It was a springtime. It would, and I went back because I wanted to find that guy, and I was thinking, what would he be up to now from, like, you know, Kentucky Fried Chicken? I don't know, you know. I think he's pretty famous now. Anyway, it was kind of during shutdown time, but I planned it because I really want to see that effect of the 3D printer and see if you could capture that resolution within a printer, because that would be really one, like, you know, NRCS has those great demonstrations, but just like, hey, here's what we should be doing, here's the nice structure, and then here's this, and then pour some water with some dye in it, you know, and just show it, or do flow through to improve maybe Darcy-Velocity equations in the soil. I don't know, just
Yeah, that's what I was gonna ask is, that it didn't work out to do the tape. I was just wondering, like, how far you went on that path.
I've been able to like open the file with like some engineering softwares where I can look the 3D and I can calculate porosity from it. The technology is just coming out now where you're able to use different media for the printing.
Were you able to do the printing with other?
I didn't get to try it
or
yet.
anything, just to like see if you can print from the tomography?
I wasn't able to, but
So,
yeah.
yeah.
I wonder, yeah.
Yeah.
Hopefully it's not compacted, it's just like some blob, but anything else?
Well, I guess I'm curious to hear a little bit more about this, where you said there's diameter essentially gets cut off for this runoff. And then also just thinking about water flow, but in a non-uniform ways, like preferential flow, how much that might alter your results.
Are you saying break down to a certain diameter, or which part were you?
So this was, yeah, so it was about the time as well.
Okay. Don't steal that, 'cause I'm working on it.
Yeah, no, you saw it out there. Yeah.
Yeah, No, I think that if I could get water stable ag test, the traditional, that Duncan one, if I could do that over time, if I could do that same thing that I do with the rainfall, looking to break down, I think I could get at that a lot better. I still need to come up with a better method to find that breakdown and of those sizes and time. I think to be more reflective of what's happening in the soil column.
Can I got one more question for you?
Yes.
You showed us series of studies that you have done. Could you give us a big picture where you're going?
I'm
I mean,
going
we can't,
no.
we can't measure intensity every minute or every 2 minutes. I mean, those kind of pretty expensive, enterprise. So where is all this information? How are you going to use it?
Hopefully I'd like to take and capture the rainfall intensity and kind of categorize those storms, right? And then I think that you can use rainfall simulators to do that job, to answer those questions of what does this shape look like? Because constant rainfall intensities now, that it's shown that it underpredicts the energy by like 60%, right? And it's because of that fluctuating and the ramping of those. So I think that there's some work that could be done there with categorizing the storms and then, setting some representative rainfall intensity dynamics that could be applied to us, to a plot and then look in the response. I think that could help answer some questions. Or the question earlier was about the larger spatial scale. I think tying it to maybe larger, not pedal transfer functions, but larger scale to be able to make those relations is needed.
Thank you.
What about Bailey's question about preferential flow? And like, how much do you think that's happening on your rainfall simulator scale plots or in something like that box inside? How do you?
Preferential this or preferential this?
Yeah.
Root networks or, I don't, it's.
Like, do you think you have a big enough area to capture that effectively? Or?
Depends. I mean, I would have to be.
It seems like it'd be missing from the box from the artificial setup.
Oh, for sure. Yeah.
About all the rainfall velocity work. Have you at all, seems like the focus has been kind of the bench seasons where there's nothing growing, but I'm wondering if you've looked at all at how the different crop canopies or continuous cover systems can kind of reduce the impact of that velocity. Because one of the ideas of continuous cover is it's like that climate adaptation, you're like dampening the direct physical effect of these heavy rainfalls. I just wonder if you've looked at that at all.
Yeah, I've tried to look at worst case scenario and be able to understand that soil response. Add in the vegetative or the canopy impacts is needed. If I was going to make estimates, I could, if you relate your kinetic energy to the soil, maybe by cover, a simple relation would be just that times 1 minus that, just to be able to percentage it out. But there's been some work on like stem flow and through fall of different, but you'd have to have the right setup. And maybe it needs to be monitored with natural, but then maybe you're just kind of left to what kind of storm and, but being able to like, or have a rainfall, set up, and maybe you could do it till a certain height, but then you may need to adjust the height to get terminal to that. I don't know.
Or you could even do, because if you had a controlled setup like you have, like just looking at the different plant species, not necessarily even going over time, but there's a lot of that you can just like look at, broadly versus.
Yeah, I mean, if you had the same slope, you could,
Exactly.
design it like that of the different.
Just to see.
It'd be a good setup.
Different plant cover and change that.
All right.
All right, let's thank Ken again.
Thanks, everyone.
We have 2 more seminars this semester.